All right, Chapter 1, Section 1, Limits and Intuitive Approach. For all intents and purposes, limits and the limiting process is going to be what takes us through the entire year of calculus. The two main components in which we discuss limits are for function values, limits, derivatives, slopes of tangent lines, and then for area under a curve. So those are our two key components when we use derivatives and antiderivatives or integrals. All right, the tangent line problem is going to be where we spend the first half of the year, and those are going to have to do with a tangent line which touches a curve at exactly one and only one spot. And then the second one will be our integrals, and that's going to be an area problem, and so we're going to be looking at the area under a curve from one point to the next. So big ideas. Okay, so let's look at tangent lines and limits. The first thing we want to remember is what a tangent line is. So in figure A, you can see that the tangent line touches at this point and only that point. In figure B, we're cutting through the graph. That is not a tangent line. And in figure C, at this point right here, we have a tangent line at that point, even though as we go on in space, it'll cut through this curve. We don't really care about that. Okay, we're only concerned at what's happening there. In figure A, take a look at it, and we're going to use two terms. We're going to use the secant line, which is just touches at any 2 points. And then what we want to notice is as we move that point, following the arrow in figure B, we move that point closer and closer to figure P. The slope of the secant line is actually getting closer and closer to that of the tangent line. Okay? So we are, in here, concerned with the slope of the tangent line, not the secant line. But if we can use the secant line to approximate, that will get us to where we need to be, and that's going to be the limiting process. So let's do an example. It says find the equation for the tangent line to the parabola at y equals x squared at the point 1, 1. So for the visual learner, which I need to be, I'm going to go ahead and I'm going to use my graph here, and I'm just going to sketch a y equals x squared, just a couple of points, and bigger dots if you need them. And there we go. And so I want to approximate the slope of the tangent line right here. So I'm looking for the slope of the tangent line right there. Okay, so remember that your tangent line touches at that one and only that one spot. And so I want to find out what the equation for that tangent line is. So what I want to do is I want to figure out, well, how could I find the slope between this point and any other point? Okay, so if I started with a secant line and I move this dot closer and closer, eventually, when the distance between those is 0, I can approximate the slope of my tangent line. So to find the slope of the tangent, I need to find the slope in general terms. So let's find a secant slope. And that would be a formula. Remember, rise over run from Algebra 1. And so we take some arbitrary point, which I don't know. I'm going to call it x, some x. And it's going to have an ordered pair, arbitrary point. So what I want to do is remember that y equals x squared is my graph. So when I plug in x, what I'm really going to get is x squared. That's my arbitrary point. I'll call that any point that I'm moving. And I know the other point is 1, 1. So if I use my slope formula and I take rise over run, so I'm going to go 1 minus x squared over 1 minus x. And I can't plug in 1. If I plug in 1 here, we have an error. That's not possible. And so that becomes the slope of my secant line. And if I were able to come up with some algebraic way to simplify that, that would be great. And so, hey, wait a second. 1 minus x, 1 plus x. I can use that to simplify. And if I do that, I can get rid of 1 as an issue here. And I end up with a secant slope of 1 plus x. And remember, I'm looking at the point where x equals 1 and y equals 1. So the x value for that secant slope, I could now plug in 1 since there's no algebraic error. And so I could come up with a formula for the slope. Or I can simply use general terms. That's the y1. And that's for any value. There's the slope of my tangent line. And that's for any x that I plug in, correct? So any x, naught, if you will. And this would be x naught, quantity squared. It looks kind of ugly. And so for me, I like to see things worked out. So I'm going to go ahead and finish it and show you where we're headed. I can plug in 1 here, in which case now I'm talking about the slope of the tangent line, because I can evaluate this, and I get the slope at that place is 2. And so now I can say, hey, now I'm looking at the slope of the tangent line at 2 is equal to 2 at the point 1, 1. And so a little bit of algebra, and I'm going to end up with y equals 2x minus 1. Okay, that's the finished product. It looks really ugly when we look at it in arbitrary terms. So this right here does not look fun to me. And remember, this right here is simplified. Okay, so when it comes to areas and limits, one of the ideas is we want to break this up into little pieces. And so when we do that, we have these rectangles. And so we want the whole area. And so in figure A, that would be the total area. And to approximate that, we would have to use these rectangles. And what you see happening is here in figure A, we have no rectangles. In figure B, we have a few rectangles. And in figure C, we have more and more rectangles. The important piece there to note is look at the amount of white space in figure B compared to figure C. So clearly, the more rectangles we have, the greater our approximation for our area will be. Again, this is a limiting process, and that limiting process will vary slightly from the limiting for the tangent line problem compared to the area problems in terms of details, but the general process is exactly the same. Okay, so here we are. We're going to talk about limits and the different methods in which you can find a limit. The first method is computational. This is using a calculator, and this is where the graphing calculator becomes extremely handy. And again, we want to find the limit at 2. And the good news here is we have a function given in the problem. And if I just plugged in 2, I could see that the limit is equal to 3. When we're talking about limits, we're talking about a function value, okay? And for those of us who don't remember, function value is the y values. So in this case, it's kind of nice because we can simply plug in 2. So we get 2 squared minus 2 plus 1, and you can see that's going to equal to 3. They don't all work out that pretty. However, you can also do it whether or not you can plug in. You can use your graphing calculator. And when we're talking about the limits, we're talking about numbers extremely close to 2, but not 2. In fact, at the number 2, we're going to use WC. Because guess what? Who cares? We don't. What matters is what's happening at very, very close to 2, not at 2. Okay, so we're looking at numbers. And so you can see in this table, these numbers are getting closer and closer and closer and closer to about 3, from less than 3 to almost 3. And the numbers on the right side, as we move from right to left, those numbers started greater than 3 and are slowly but surely approaching the value 3. If we had to guess based on this table, we'd say 3, in this case, we can just plug it in, and we can also see that the value is exactly 3. Okay, so informally, what we want to say is we want to be able to read this. So the limit as x approaches a for some function is equal to L, or the limit. And so as x approaches some value, the y values are approaching some finite value. That would be its limit. Example, the last problem, we had x squared minus x plus 1. It was x squared minus x plus 1. Okay. Not 3 yet. And we would say f of 2 would mean to plug in 2. And if I can simply substitute it in, it turns out that that function value is 3, and therefore the limit is 3. When we write it this way, we say the limit as x approaches 2 of some function. In this case, it's equal to 3. It doesn't actually matter if we can plug that in, because we're going to have several methods by which we can evaluate that. Again, we're looking at close to A. Who cares what's actually happening here? At 2, we want to know what's happening at really, really close to 2. So we want to use numerical evidence to make a conjecture about the value of the function, the limit, as x approaches 1 of x minus 1 over the square root of x minus 1. Okay, the first thing you should be seeing is I can't just plug in 1. Okay, so we want to take substitution off the table. So I can't just plug in 1. So my only other option is to use my graphing calculator. And so I want to pull that up, and I want to use my graphing calculator now so that I can evaluate that function. And again, we're looking at the quantity x minus 1, go back, minus 1, that whole quantity divided by the quantity, the square root of x minus 1. Okay, so there's my graph, and now I want to look at it. And there's a picture. And again, remember, I'm looking for what's happening at close to 1 on either side. Close to 1. Okay? So I need to look at my data table, but before I do that, I want to go ahead and say, well, look at my graph right here in the center of the screen. Look at error, 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 1, error. So I can't actually be at 1 because it says error. So I want to come over here and I want to say, okay, well, let me close that. I want to come over here and I want to say, well, what happens if I look at values extremely close to 1? And extremely close to 1, 1 would be in the center. So we're looking at numbers that are greater, like 1.00001, 1.001, 1.01, 1.1. So we want to get infinitely close to 0, or 1 in this case, from the top, as well as from the bottom. And we want to see what's happening. So when we go back to our graphing calculator, we want to make sure we change our table. And let's have our table start at 0.9. And then we want our table to go up, let's say by 0.02. And that'll give us a fairly good. And then let's take a look at the table. So at 0.9, we're at 1.94. At 0.92, we're at 1.95. What do you see happening to these values as we go from here to here? They're approaching some number. On my screen, if I look here, it looks like it's just over 2. So if I were going to give a guess, my guess would be 2. Okay? So use numerical evidence. You can use your graphing calculator, and you can simply transfer that data into this space here. Okay? Use numerical evidence to make a conjecture about the value of the limit as x approaches 0 of sine x over x. So go ahead now and enter that into your calculator, and let's see what you can get. Do that now. Okay, so you would enter sine x divided by x into your graphing calculator, and then take a look at the table. And you can see there on my large screen that there is a picture of the graph. You should have something that looks like a little hill. And now when I take a look at my table, I want to take a look at what's happening to those values as they get extremely close to 1 or at 0. So let me adjust my window, my table, and I want to look at numbers close to 0. And there we go. So let's take a look at my table now. And I can't be 0 because the bottom blows up. But what happens? As I approach 0 from the left, the values appear to be 1. And as I approach 0 from the right, the values also appear to be 1. So my guess would be 1. And again, your evidence will include an XY table, in which case you would list out values. And remember, at 1, who cares, right? We're looking at what happens to, at 0. We're looking at what happens to this as we are slightly larger and slightly smaller, right? We want to see what's happening as we get super close to 0 without actually being 0. Okay, one-sided limits. Now, in order for a function to actually have a limit, the left and the right-hand limits have to exist. Personally, call it the finger test, because I want to put my finger on the graph to the left and the right of the value that I'm looking at. So in this case, I'm looking at x equals 0. That's this line right here. So I want to put one finger on the graph to the left, and I want to put one finger on the graph to the right. I want to take these fingers and I want to move them in until I get really, 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 really close to x equals 0. And so what I want to take a look at is as I move my finger this way, this value is approaching -1. And so the limit as x approaches 0 from the left, that's the green, is -1. Now, put my finger on the graph to the right, move it to the left until I approach 0. Notice the open circle. And as I do that, I'm actually pointing at the value 1. So the limit from the right, and this is red, the limit as x approaches 0 from the right. The limit as x approaches 0 from the left. Okay? So one-sided limits can exist. And what we want to see is if the function limit exists. And that's going to lead us to the next slide, which says that you can only have a limit if the limit of each side exists and is equal, which means the left and the right have to be equal to the same number. Okay? If they are not, you cannot have the limit as x approaches a for any function. So when we go back here and look at this slide, -1 is not equal to 1. Therefore, the limit as x approaches 0 of the absolute value of x divided by x does not exist. Okay? The left and right hand limits are not equal. So what this is telling you is if the left and the right are not equal, if the limit as x approaches a from the right of some function does not equal the limit as x approaches a from the left of that function, then the limit as x approaches a of f of x does not exist. Okay? Called the finger test. Your fingers have to be pointing to the same y value. Let's take a look and see. Okay, again, here it is, formal terms. If and only if, IFF, okay? So we just did this one, and the limit as x approaches 0 from the left of that function was equal to -1. Then we looked at the limit as x approaches 0 from the right of that same function, and we got 1. Since they are not equal, the limit as x approaches 0 of f of x does not exist. Okay, the left and right hand limit must be equal to each other. Okay, for the functions in this figure, find the one-sided and two-sided limits as, at x equals a if they exist. Go ahead and take a minute and try those on your own. Okay, I'm going to go ahead and go through figure 1 first. So figure 1, the limit as x approaches a from the left, that's starting here and approaching from the left side of some function, and I got 1. Now I'm going to take a look at the limit as x approaches a from the right. This is to the right, and on the graph I'm tracing, and I'm going to end up pointing to the y value of 3. And now I look at it and I say, hey, here are my one-sided limits. The two-sided limit does not exist. So the limit as x approaches a, notice no right or left, of that function does not exist. And the reason is 1 is not equal to 3. Okay? So now when I come over here, figure 2, the limit as x approaches a from the left is equal to 1. And all limit as x approaches a from the left of that function is equal to 1. Now on the right side, and I approach from the right, going towards my a value, I end up pointing to 3. So the limit as x approaches a from the right of this function is equal to 3. And guess what? Does not exist. The limit of f of x, oops, out of space. Let me rewrite that. And I'll rewrite that up here. So the limit as x approaches a of this function does not exist. And again, finger here, they're not touching. It does not exist. Now easily here, as we come in, we see the limits approaching 1. We see the limits approaching 3. 1 does not equal 3. Therefore, the one-sided limits exist, but the two-sided limit does not exist. Okay? That would be a graphical analysis of a function so that you can determine limits. Finger test. Left side, right side. Move them, move them. If they're going to the same y value, you will have a limit. For the functions in figure shown here, find the one-sided and two-sided limits at x equals a if they exist. Okay, so go ahead and pause now and write down your answers. All right, so in figure 1, following along the left side towards a, I get a limit of 2. It's pointing to the y value of 2. From the right, as I get extremely close, I'm pointing to the y value of 2. So each of the right hand and the left hand are equal to each other. They're both pointing to the value 2. So now I'm going to go ahead and say as x approaches a of some function is equal to 2. And now I'm going to go ahead and take a look at the second figure. And as I approach on the graph from the left, I am pointing to a y value of 2. From the right side, as I approach on the line towards a, I'm also pointing to the value of 2. This dot right here, not on my graph. It's a point in space right now. But as both of these arrows are clearly pointing to the value of 2, we say that the limit as x approaches a of some function is equal to 2. Okay? And now we're going to do it again. Pen on the left side, trace, you're pointing to a y value of 2. Pen on the right side, trace, pointing to a y value of 2. Therefore, we can say the limit as x approaches a of some function is equal to 2. A couple of things I want to point out now. The first one, this was an open circle. It doesn't matter what's actually happening at 2. We want to look at numbers as we approach 2. At 2, our data table is who cares. Again, we have an open circle here with some dot out here in space. Again, data table. Something like this. We're looking at values. Who cares what's happening at the number 2? In the third example, we had a continuous function. And again, we don't care what's actually happening at 2. Who cares? We only care about what's happening as we approach 2. All right, infinite limits. This is a infinite. We use limits as finite values. Neither infinity nor negative infinity is a finite value, but we can still use that to describe the behavior of the ends of our graph when it comes to any specified x value. So notice, as x approaches 0 from the right, starting here, approaching 0 from the right, this is going upwards towards positive infinity. And that as we approach 0 from the left, we are going down towards negative infinity. It just means that it's going to increase or decrease with no limit in sight. Okay, so again, we're talking about end behavior, okay, end behavior. If the end behavior is the same, then we can say the limit exists. If the end behavior is not the same, then the limit does not exist. So you can use a positive infinity equal to a positive infinity to say that the limit is positive infinity, which just means that it's going to increase without bounds. Okay? Negative and negative, rather than saying it doesn't have a limit, you can simply say that its limit is negative infinity, which means it's going to decrease without bounds. Okay, for the functions in the picture below, use appropriate notation and describe the limits as x approaches a. Okay, so from the left, it's going to negative infinity. From the right, it's going to positive infinity. And therefore, we would say that the two-sided limit in this case does not exist because you have a positive infinity and a negative infinity. Okay, here's A. So from the left of A, tracing the graph, we're pointing to a plus infinity. From the right, on the graph, we're pointing to a plus infinity. And so here we could say a positive infinity, which means it's going to increase without bounds. Okay, we come over here. Here is A. Again, we don't actually care what's happening at A, only at values very, very close. From the left, we follow the graph, tracing, we go to plus infinity. Starting on the left, starting on the right, tracing the graph towards A, we're going to negative infinity. Okay? Again, a positive infinity and a negative infinity does not exist. They're not the same. And our fourth example, from the left of A, approaching A, on the graph, approaching A, who cares what's happening there? Now, from the right, on the graph, tracing towards A, we get another negative infinity. Since these are both negative infinity, we can say negative infinity. Vertical asymptotes. Just a quick review of vertical asymptotes. Remember, we don't cross vertical asymptotes. Those are places where a function is undefined. Okay, where a function is undefined. So, and I'm saying function in each of these pictures. We have a function because it passes the vertical line test. And so what ends up happening as x approaches a from the right, we're going to negative infinity. As x approaches a from the left, negative infinity. We're looking as we approach a from the right and as we approach a from the left. Okay, notice we're talking about being on either side of a. This is the right side. This is the left side of a. Okay, referring to the diagrams below, take a look at these. We want to see what happens. These are given information. Okay, given information. And so here we are in this one, and you can see that as these come in towards 0, and again, we're talking about 0. All of these log graphs, every one of them is pointing to negative infinity. Okay? Important note here, we're talking about where b is greater than 1. Okay, b is greater than 1. In figure 0.3.11, when we have these vertical asymptotes, we have them at 1 and negative 1. And now we want to take a look at those, and you want to see what happens. So as I go approaching negative 1 from the left, I'm at negative infinity. As I approach it from the right, I'm at positive infinity. The limit does not exist on that. Okay? And now, if I come over to 1, as I approach it from the left, I'm going to negative infinity. And as I approach it from the right, I'm going to positive infinity. Okay? So those vertical asymptotes can or can't have limits. They may or may not have them. In this case, both of these two-sided limits do not exist. Okay? The right-hand limits exist, the left-hand limit exists, but there is not a two-sided limit. Negative infinity is not equal to positive infinity. Positive, negative does not exist. At negative, positive does not exist. All right, you're now going to take a chance and do some of these on your own. Again, we want you practicing these on your own. In your book, if this is hard to read, please visit page 76. And the answers are given on page 80. Remember, you should look at the answers after you have tried the problems. Okay? Now, one of the things we'd like you to do, in addition to having completed these practice exercises, you may want to go back and take a look at some of the slides along the way and see if there's anything you don't understand or anything that was confusing. Okay? Anything that you don't understand, anything that seems confusing. And write down a question or two in your notes so that tomorrow when you guys come into class, you have something to discuss with your peers. Good luck.